Kia ora and welcome back. In this video we're going to talk about the first isomorphism theorem. Now this is a theorem that tells us that when we've got a group in a homomorphism, that when we pass our group through the homomorphism we get what's called a homomorphic image of our group. And the first isomorphism theorem tells us that this homomorphic image is isomorphic to a factor group of the group itself. So that when we pass a group through a homomorphism, we get kind of like a simplified picture of some aspects of the group in that homomorphic image that we can study as a factor group of the group. Okay, so here's the theorem. It's the first isomorphism theorem, and it says if we've got a homomorphism phi from G to G bar, then we can define a mapping from the factor group of the kernel in G to phi of G, which is the set of all things of G mapped through phi, called the homomorphic image of G. So the mapping is you take an element little g, form its coset G kernel phi, and you map that coset to phi of little g itself. And the theorem says that that mapping is an isomorphism, which means that the factor group of the kernel is isomorphic to the image of G through phi. Okay, so it's a lot of words and a lot of technical language there, so it'll take a little bit to sink in exactly what this means. But let's just start attacking a proof of this, because it's actually not that difficult, before we sort of explore some of the ramifications of it. Okay, so we're going to prove this. The proof is essentially just asking us to show that a particular mapping is an isomorphism. We know how to do these proofs, so we'll just start by setting up the function and giving it a name, and then just showing that it's an isomorphism, i.e. showing its operation preserving one-to-one and onto, blah, blah, blah. Okay, so we'll let psi denote the mapping that we're talking about. So let's just have psi denote the mapping specified there, which is the coset G kernel phi is mapped to phi of G. Okay, so first off, psi is well defined. Okay, from our homomorphism element properties. Okay, and that's the one, property number 5, that says that if two things map to the same element, they're definitely in the same coset. Okay, so we can't get different coset representatives mapping to different elements. That all works from our properties we've talked about previously. Okay, so it's a well-defined mapping. We don't need to bother about proving that part of it. So that's the element property 5. Let's just make a little note so we remember what that was. That's the one that says phi of A equals phi of B if and only if the two cosets are the same thing. A kernel phi equals B kernel phi. Okay, and we also get from this argument that it's one-to-one also, is similarly one-to-one. Okay, you can see that if I assume that phi of A equals phi of B, that's the one-to-oneness, then I'll get the cosets the same, and that just makes sense. Also, psi is onto, by construction, we can take any little element G from our group and get phi of G, so there's nothing else to do there. So the bijection part of it comes pretty straightforwardly. We just need to show that it's operation preserving, and then we'll be done. So to show it's operation preserving, we need to take psi, and we need to stick in two cosets combined together. So psi kernel phi, x kernel phi, and y kernel phi, and show that we get psi of each one composed afterwards in our G bar. Okay, so that is, we know that to combine two cosets together, we just multiply the representatives. So that's going to be equal to psi of x, y kernel phi, because that's our composition rule for factor groups. And by definition, this mapping here is psi. So if I take this particular coset xy kernel phi, that's going to map to phi of xy. But phi of xy, well, phi is a homomorphism itself, so that will be phi of x, phi of y. So just make sure you're clear on the differences between psi and phi here. Phi is our homomorphism that we started with. and psi is this mapping from the cosets to phi of g. Okay, so the mapping gives us phi of something afterwards. That's why we switched from using psi to phi here. And then phi of xy, well, that just equals, let's give us a little more space, we'll go over here. That's going to equal psi of x kernel phi, psi of y kernel phi. Alright, so it's just applying our definition from above, and therefore psi is operation preserving, and hence an isomorphism. Okay, that's great. So we have, even though we haven't really discussed this theorem particularly much yet, the actual proof of it was fairly straightforward. So now we know that this particular mapping is an isomorphism, which means that we can treat these two things as isomorphic and start to draw some conclusions about this. Okay, so first off, we get to note what this says if we take a homomorphic image of our group. So this thing here, remember, is a homomorphic image. Right, so no matter what homomorphism we choose, we call that thing a homomorphic image of G. And what this theorem is telling us is that the information about how that image behaves is contained within a factor group of G. So it says all information about homomorphic images of G. Let's put phi of G is contained in the factor groups of G. So that says that when I take a homomorphic image of a group, really what I'm seeing is some intrinsic property of the group represented in my new space, factor groups of G. Because actually it's just a property of a factor group of G that we're going to see in our homomorphic image. Alright, so also we can state a corollary to this theorem, which says, it says that if phi is a homomorphism from a finite group G to G bar, then the size of phi of G, let's just tidy that up slightly, G, divides both the order of G itself, let's not make my G's look like A's, and also the order of G bar. Why is this? Well, we know that phi of G is isomorphic to G factor group of kernel phi, which means the order of G is therefore equal to, the order of phi of G how do we figure that? Well, because it's isomorphic to the factor group, it's just going to have the number of elements of G divided by the number of elements in the kernel. And hence the order of phi of G divides the order of G. And similarly, we know that phi of G is a subgroup of G bar. So by Lagrange's theorem, orders of subgroups always divide orders of groups. The order of phi of G divides the order of G bar also. Okay. So it's probably a good time to now look at an example and just see how the various pieces of the first isomorphism theorem actually fit together. So we're going to go back to our homomorphism, which takes the integers onto the integers mod n by literally just taking x mod n. Okay, so from our previous work we've done on this problem, we know that the kernel of phi is the cyclic subgroup generated by n. So if we're going to translate the language of our theorem into the language of this example, the factor group of the kernel here is the factor group of Z, quotiented with the cyclic subgroup generated by n, and we know that this is isomorphic to phi of z, which we know is equal to Zn. Alright, so the first isomorphism theorem is telling us that this is isomorphic to Zn like this. Alright, we can actually draw a little bit of a diagram to illustrate how this one works. So what this is saying is we take a group Z and we pass it through phi, we get phi of Z, which is equal to Zn. Now alternatively, we can go to the factor group by doing a different mapping along here, defined by gamma of x is just equal to the coset represented by x. Now if we do that, then that mapping gamma takes us into the factor group, and then the psi from our previous proof, that's the isomorphism between the factor group and the homomorphic image, that is going to be given by psi of a coset is defined to be phi of x. So this diagram kind of is a nice graphical representation of our theorem, because what we have here is that phi is equal to the composition of those two functions. Okay, so first one that happens is gamma, so it goes on the right hand side, and the second one is psi. So we can see that phi is the composition of psi and gamma. We say this diagram is commutative. Okay, it doesn't matter which pathway you take through the mappings, you can either go directly to your homomorphic image, or you can go this way and you'll get the same result by going through these two different things. And we could redraw the diagram for our general case where we have a group G, we send it through phi, we get phi of G, or we go through a mapping gamma. Let's just define what that was in a second, which takes us into our factor group, and then we go through that mapping psi back to phi of G. So this mapping gamma is what's called the natural mapping into factor group of the kernel. And it is G is mapped onto G kernel phi. So no matter which way we do it, we are always going to get that our mapping phi is also equal to the composition of those two mappings there. Okay, so that may be helpful to think of it slightly pictorially like this. We've got these two different ways of mapping, and what the theorem is telling us is that these two groups are isomorphic, which is what we've been talking about. We're going to complete our section of theorems with one more, and this kind of is a nice little tie-in. It says that every normal subgroup of a group G is a kernel. We've already established that kernels of homomorphisms are always normal, but now we're saying that all normal subgroups are the kernel of some homomorphism. So the theorem tells us that every normal subgroup is a kernel of a homomorphism, and helpfully it also tells us what the homomorphism is that it is the kernel of. So you take a subgroup N, and it's the kernel of the mapping from G into the factor group of G mod N. Okay, and it's the same kind of natural mapping we used before. You map the element G onto the coset of the subgroup that it's represented by. Alright, so let's just quickly show this is the case. So we'll define gamma to be the mapping from G into the factor group of N and G by gamma of G equals Gn. Okay, this is called the natural homomorphism. Then, gamma of xy is equal to xy n, which equals xn yn, which equals gamma of x, gamma of y. Okay, so gamma is definitely a homomorphism because it preserves the group operation. So gamma is a homomorphism. So far so good. So now we've established that this is definitely a homomorphism into the factor group of n in G. Now we need to double check that the kernel of it is indeed n. So the kernel of gamma is equal to the set of all elements in my group G such that gamma of G is equal to the identity of my quotient group, my factor group. And we know the identity is this normal subgroup itself. So that is my kernel. So gamma of G is equal to Gn, which equals n if and only if G is a member of n. So the kernel of gamma is just n itself. Okay, the only things that map directly into n are elements of n, and so the kernel is n. So that's cool. So once I've got my normal subgroup, I can set up the factor group and the homomorphism into that factor group defined naturally like this has the kernel n. So all normal subgroups are kernels of some homomorphism. Alright, so let's look at an example of what a homomorphic image of a group can actually tell us about the group itself. Because kind of the point of homomorphisms is to help us understand how a group works by essentially studying homomorphic images and using that to conclude something about the group itself. So for the example we're going to look at here, we've got a group of order 60, and we're going to suppose that we have found a homomorphism that gives us an image of order 12 that's cyclic. So what can we then say about G? Alright, so a few pieces of information here. If the homomorphic image has order 12, it means that the kernel of phi must have 5 things in it, right? Because there are going to be 5 pieces of the factor group of G, 12 pieces of the factor group of G that map to these this image of order 12. So first off, the kernel of phi must have order 5, as this would partition a group into 12 pieces. Okay, so looking at our homomorphic image, it's a cyclic group of order 12. So we know a lot about cyclic groups. In particular, we know that cyclic groups are abelian, and we know what all the subgroups of it are. So let H bar be the cyclic subgroup in question. Then we know that all subgroups are cyclic because all subgroups of a cyclic group are always cyclic. And because cyclic groups are abelian, all subgroups of abelian groups are also normal in H bar. So we've automatically got a bunch of normal subgroups of H bar that we can do something with. What's more, we know which subgroups they are because they're just the factors of 12. So the only possibilities are groups of order 1, 2, 3, and the factors of 12, 6, and 12. Now we know that if we have a normal subgroup and we backpropagate it through our homomorphism, i.e. we find its pre-image, We showed during our subgroup properties that this will give us a normal subgroup in G. So hence, given that our homomorphism is 5 to 1, G must have normal subgroups of order 5, just 5 times each of these, 10, 15, 20, 30, and 60. Alright, so knowing that our homomorphic image was cyclic gave us some information about the normal subgroups in G. So we used the fact that we know about how to figure out subgroups of cyclic groups, and we know that subgroups of abelian groups are normal, and we use that information to pass it back through our homomorphism, i.e. going 1 to 5 if you like. There are 5 because the mapping was 5 to 1. And our homomorphism subgroup properties guarantee for us that therefore there will be normal subgroups of order 5, 10, 15, 20, 30, and 60 in G. Okay, so, and we use the tool of our homomorphism to help us to discover this fact. We'll do one last example, and this is the so-called wrapping function. It's a function that takes real numbers onto complex numbers, and it's defined by w of x is equal to cosine x plus I sine x. So essentially it's going to take a number and it's going to put it onto the unit circle. So let's just see if we can fit together the pieces of the first isomorphism theorem to find out how this actually works. Okay, so we need to find the kernel of this mapping. Oh, so you should probably first check that it's a homomorphism. So I'll let you check that as an exercise. Just need to check that it preserves the group operation. So we're in the complex numbers under multiplication and the real numbers under addition there. So that should be C star for multiplication. Okay, so this maps it onto the unit circle in the complex plane, so which is also a subgroup of the complex numbers under multiplication. Alright, so what is the identity of our complex numbers under multiplication? Well, that's 1. So we'll find the kernel now. So essentially we're looking for all x such that w of x equals 1. And this means x is a multiple of 2 pi. So the kernel of our mapping is just the cyclic subgroup generated by 2 pi, i.e. all multiples of 2 pi. Therefore, by the first isomorphism theorem, the factor group of the reals with the kernel of our mapping, which is the cyclic subgroup generated by 2 pi, is isomorphic to the homomorphic image, which is just the unit circle. So w of just 0 to 2 pi, which is called the circle group. Okay, and so that kind of concludes that example. So we can see that we can use this first isomorphism theorem to make connections like these, and also to probe groups to understand more about them. Alright, so that's enough for this video. We will return next time with our new topic, which is rings. So we'll catch you later.